In this devlog, we'll give some short updates in terms of the progress on the artificial neural network project written in C++. So I understand there's been a long hiatus since the previous video, although some code has been included in the project to mainly work forward to the next two functions, which is feed forward and backpropagation. So before I discuss the project, we can probably notice that I'm using a different desktop environment. I'm now using GNOME 3 instead of Unity on Ubuntu 16.10, primarily following the recent changes in terms of the decisions that Ubuntu is making towards their platform, which is basically the famous April 5 announcement by Mark Shuttleworth that they're now dropping the Unity project as well as Mirror and going back to GNOME for Ubuntu 18.04, which is due out next year. So there are some good and bad points towards this particular decision. The good, of course, being it will lessen fragmentation and Ubuntu can focus on contributing, like using their developer talents to contribute back to the community the way it was originally designed, and the reason why it became so popular in terms of the development or in terms of developers around the world. So it's nice that they're going back to GNOME. It also saddens me because I was actually fond of the Unity desktop environment. Although GNOME 3 still works for me, it's actually very similar. You have some sort of dash working, and you have a pretty modern looking interface. Plus, I think the terminal looks very futuristic and very nice, at least for the stock terminal. Right, so that was one thing I worked on recently, was basically to transition my current setup from Unity to GNOME 3, and it's working out pretty okay, I guess. The second major change is that, which is now related to the project, is that I moved the project to a GitHub repository under the handle ralampay/ANN. So I have the some commits right here, then some initial commits, and basically it would be easier for me to track some changes, or in case something happens to my laptop, then I can actually pull the project there as well. So it's up on GitHub, and for every change that we do in a video or outside the video, I'll probably push it here. Right? I've also set up my workflow to include Timoxinator. I've actually been using Timoxinator for quite some time now, but basically it's an excellent tool for streamlining your workflows by opening multiple Tmox windows using a configuration file. So for this particular project, I'm using two Tmox windows. Right? One for the actual editor and one for the compiler, which will automatically compile my code when I open up the project. Okay, so now moving to the code proper. You still have your basic classes. I think I left off with the layer class, which had some functions, matrixify vals, which returns a matrix form containing the values of the neurons for this particular layer in a matrix form. So that's just a single row with a bunch of double values, wherein the number of columns for that matrix will be the number of neurons in this layer. I've also created a generic neural network class, okay, which will hold the entire workflow for this neural network and make use of the different components that we'll be creating. But probably the newest addition to the class that I wasn't able to do a video of was the multiply matrix class. So I've adapted this technique from my work coding web applications in Ruby on Rails, wherein we treat a class as a particular business rule or as a particular function. In this case, I need a function called multiply matrix, and I know there are a lot of libraries out there that also does matrix multiplication in probably more efficient manner than mine. However, again, this is for academic purposes, so I'd like to study the very fine details on how things actually move around a particular algorithm or a concept. So multiplying a matrix is one of those key concepts in neural networks, so I decided to create a class out of it. And since this one follows the command pattern, the idea is that you have a class whose class name is named after the function you'd like to achieve, in this case, multiplying two matrices together. It has a constructor which will allow you to pass the needed values for this particular objective, as well as an execute class, which will return the result of this operation. Okay, so try to think of it as a function in the form of a class, something like an object-oriented function approach. Okay, so in this case, it returns a pointer to a matrix. And the algorithm is the most basic algorithm in terms of matrix multiplication, wherein we loop through, it's otherwise called as the IJK matrix multiplication. It's a brute force approach wherein we loop through the rows, and for each loop in that row, we loop through the columns, and for each of those columns, we have a counter k that loops through the number of rows for a given for the second matrix, right? For the second matrix B, right? So it ensures that if that matrix follows the proper rules of matrix multiplication, wherein the number of rows is equal to the number of columns, the number of rows in the first matrix A is equal to the number of columns in the second matrix B, then this algorithm or this function will actually work. So in the inner loop here, you have k as the counter to the number of rows in the second matrix, wherein we simply multiply the value at the ikth index of the first matrix multiplied by the kj index of the second matrix. And once we have that, we perform a summation against this inner loop. And whatever that new val is, we set it as the new val for the resulting matrix. Right. Well, actually, it's not a summation, but rather it adds up all the values of whatever value is in the ij index of the C matrix. So when we initialize when we initialize this function, it automatically creates the resulting matrix as an empty matrix where the size is equal to the number of rows for the first matrix, and in terms of rows, right? And the size of the columns is equal to the number of columns for the second matrix. And we can call it by something like new multiply matrix pass matrix A plus matrix B dot execute or arrow execute, and it will return the resulting C matrix. The reason why I also did this is that I can play around with this particular class and do things like probably in the future GPU, wherein I perform a more efficient way on multiplying matrices. Okay, I'm also doing this. I'm not sure if I should continue with this particular class. I also have another pattern, call this command pattern approach class to convert a matrix to a vector, which might be useful later on. But basically, the way it works is that you pass a matrix to it, and it will simply loop through all the rows and all the columns of that matrix and return a resulting vector of doubles. Okay, so those were the two main additions to this particular project, and I guess the next thing would be to discuss the feed-forward function, wherein the idea is that you loop through each layer. Okay, you loop through each layer starting with the input layer, and then get the input and multiply it by the set of weights for multiply it by the set of weights for the leftmost layer to the right layer, to the layer right after that particular layer. So if we had a neural network of 3 layers, wherein you had an input layer, a hidden layer, and an output layer, the first multiplication, matrix multiplication that will occur to get the values of the hidden layer will be to multiply the input, right? The input vector of values or matrix of values multiplied by the weight matrix between the input and the hidden layer. So that's how it's being done in this case. So here we're looping, right? We're looping through all the layers found in this neural network, okay, from size, the size of that layer, -1. The reason why we put the -1 here is so that we will only loop from the input to the hidden layers and not reach the output layer. The reason behind that is that we won't perform any operation to the output layer because the output layer is already the result of the feed-forward operation of a neural network. So we loop from 0 until layer size -1, right? And we get we perform this function called get neuron matrix at index I. So I here refers to the index of the layer for this particular neural network. So a neural network will have multiple layers. We want to get the ith layer of this neural network and return its neuron matrix. Okay, so at the first loop, this get neuron matrix at index I, wherein I is equal to 0, will serve as the input layer values in the form of a matrix. So when we look at the implementation for get neuron matrix in the neural network class, all it's actually doing is, all it's actually doing is that it's using the index to get the layers, right? To get the layer at that given index and return its matrixified values or the raw values of this particular layer without any activation, without any derivation. So that's what it typically does. And we have a checker here. So if I is not equal to 0, then instead of getting the raw values of this particular set of neurons in this layer I, at index I, we get instead the activated neuron matrix for the layer at index I. So if I is equal to 0, it will return the raw values. Else, all other values between the input and the output layer will return the activated versions of these values in the form of a matrix. And again, we want it in matrix form so that we can easily multiply those two matrices by the weight matrix for this particular layer, as we can see here in line number 11. So matrix A will be the input, right, depending on where you currently are in the neural network, and matrix B will be the weight matrix for this particular neural network. So we also make use of that index I. It's also the reason why we have this layers.size -1, because if we only had this layers.size, then we wouldn't have a set of weight matrices when we reach the output layer, because the size of the weight matrix or the set of weight matrices inside the neural network will always be the size of the layers -1. Okay, so I hope that made sense, because we're looping, we're still using that same index I as a counter to determine how we get the weight matrix as we transition in a feed-forward approach from the input layer to the last hidden layer. Okay, so once we have those two matrices, we multiply them, right, using our command pattern multiply matrix class, and store it in a new matrix C. Now, given that result, I can convert it to a set of double values. So from matrix form C, I can convert it to a list of double values by looping through the number of columns for that matrix and getting the values where row is always equal to 0 and pushing it to that particular list of values. So yes, there may be some redundancy here, But basically what I'm trying to do is I'm trying to create a vector result out of multiplying the values from a given layer to its corresponding weight matrix. Okay. And basically that's where I currently am in terms of development of this neural network. So the next thing that I'd like to do is, assuming that we get these values, we'd like to set it for the as the values for the neurons for the next layer. So if we were in the input layer, the result of C will be the values for the neurons in the first hidden layer. Okay, where in the first hidden layer can be accessed by the I+1 index if we were using the I variable in our current loop. Okay. In fact, I can probably do something like this. Just check my neural network class again. Okay, I don't have a setter for the I don't have a setter for the layers, so I should probably create that method first. Okay, I can have something like void set neuron value for some given index layer. So from some given index, so we know where we actually are, and the actual value, double val, right? Let me see. Index will refer to the index or the layer index. So I'll put probably something like index layer, as well as an index to the neuron for that particular layer. So I'll say something like index neuron, right? And finally, the value for that index neuron. So what this will do is, let me see if I can try to program it in the header file. So something like this layers at index layer, right? And then I can get for a given layer, I know I have a function called get neurons, but this one will return a value, right? This one will return a vector of neurons, which we don't want. What we simply want is to set the value given some index I, which refers to the index of the neuron for this given layer, and a double value which refers to the value for that particular neuron. Okay, so if you look at the implementation for that, set val, right? Actually, this one is a buggy implementation. So I say something like this neurons at I set val v, which is the new value for this given neuron. Okay, so I do something like this layers at index layer, and then I say set val. Check if that's correct function. Set val, right? Set val at index I, which is the neuron index, and the new value for that neuron index. Okay, so my set neuron value will take in the index layer for this neural network, the index of the neuron for this particular layer index, or for this layer at index layer, and the new value for that neuron in this particular layer. So I hope that made sense, and I hope it works. So let's try that out. Neural network.cpp. Right, so push everything right there, and it will continue its own cycle until it reaches the hidden layer, or rather the output layer. However, it means I don't really need this vals. I can say this. What's that method again? Neural network. I can easily forget things. Set neuron value, right? So this set neuron value. A bit too zoomed in. Okay, so this set neuron value at index I+1, right? Because I want to set the value in the next layer throughout this iteration, set value I plus 1, the index neuron will be the column index. Right, column index for this particular loop as the value of the C result. So get value 0 C index. Okay. So this way I won't need this vector of vals, since I have a method called set neuron value, which looks at the next layer, which should store the result of multiplying matrix A and B at C index. The next layer, I plus 1, the neuron index, which is defined by the number of columns for matrix C, right? And the actual value, which is from C matrix, get value at row 0, because this is only a matrix with a single row, and C index. Okay, so it proceeds to the loop, and then in the next loop where I is equal to 1, since I is not 0, meaning it's not in the input layer, then I will get the activated version of the neural network of the layer at index I for this neural network, and set that as the value for matrix A, and then proceed to get the weight matrix and store it as matrix B, which will be the weight matrix to the right of the current layer, which is also the same index as the current looping for the set of layers for this neural network. Okay, so this way we're doing a systematic way of moving forward, or of feed forwarding our values from the input layer down to the output layer. Okay, so to try that out, we'll try to test it with a bunch of values. So in our neural network class, let me just review the constructor. We pass a topology, right, which is a vector of values, and then we can set the current input value, and then we can perform a feed forward function, right, which will perform those matrix multiplications and finally get a result. So let's try that out. In our main function, we'll hard code a bunch of values. So let's say that we have a vector of doubles, which will be our input, and we'll push in a bunch of values. Let's say 1, 0, and 1. And we also have a topology of a very simple neural network wherein the size of the input is 3. So we say something like push back 3, and for the hidden layers we'll just have 2 neurons in the hidden layer and 1 neuron in the output layer. So it's a 3-to-1 topology that takes in an input size of 3, a hidden layer with size 2, and an output layer of size 1. Okay. And when we initialize that neural network, so we have neural network NN, more specifically new neural network, and pass in the topology to it. Then we say set current input to be the input, and we perform a feed forward. Okay, so let's see if this works. If it compiles. Oops, sorry. Neural network. Sorry, neural network. No candidate. Let's see. Okay, so apparently I called the constructor incorrectly, which is weird. Oh, sorry. It should be a vector of integers rather than a vector of doubles for the topology. Okay. Right. So it compiled, so I guess everything should be in order. Let's try to run it. There is no output yet, so it will not print out anything. So if I look at the neural network HPP class, I believe I have a value here. Right. I have a function here called print to console. So what print to console does is that it tries to print the current values per layer. So it loops through each layer, displays some sort of layer index, displays the current matrix values. Okay, so if it were in the input layer, it will just get the normal raw values by using matrixify vals, print to console. Else it will get the hidden layers until the output layer and print out its activated values and try to print it out in the console. Again, we have matrix M, right, which has its own print to console function. Let's see, print to console. Right, that simply just prints out the matrix, in the matrix form, right? Okay, so let's test that out and see if it's actually working. So what I'll do is that in the main function, I'll say nn print to console, or neural network print to console. Let's compile that again, clear things out so we have some space, and we can have the following results. So we have a 3 size in the first layer, 2 neurons in the second layer, and finally 1 neuron in the output layer. So let's keep running it. It will have a bunch of random values since the weights are initialized randomly. Yes, I think this is already working. To make it more robust, then probably in my neural network class, we can also print out the weights that that were used in this particular neural network, just so we can validate the results. See, so as scientists, we of course have to evaluate the results, not just because it's giving out a particular output and it compiles well doesn't mean it's correct. It could be incorrect, and I'm not sure if it is. It actually is. All right, so let's just put a border here. I'll put it right there, and you can say something like let's see, if I is not equal to this layers dot size minus 1, because again the number of weight matrices in each layer for a neural network, or rather number of matrices of weight matrices in a neural network is equal to the number of layers minus 1. So if I is not equal to this layers dot size, actually minus 2, I believe, minus 2, right? If it's 3 to 1, then size, we have 3 layers, 3 minus 1 is 2, we should only have 2 weight matrices, so 3 minus 2 is 1. So if I is not equal to 1, this is a pickle. I is not equal to 1. I think this should only be minus 1. Alright, or if I is less than, right, I think this should be if I is less than this layers dot size minus 1, then print out the weight matrix. So this weight matrix, I have a getter for get weight matrix, right? So this get weight matrix at index I, this one returns a matrix, right? So since it's also a matrix, I can say print to console. So I can have something like weight matrix at index I. So let's see if this is correct. Okay, so weight matrix right there, weight matrix right here, right? So it looped in correctly. Okay, so I'd like to validate if my feed forward is actually working correctly. What we did is we took this layer, turned it to a matrix, multiplied it by this weight matrix, and whatever the result is, we stored it in the next layer, took its activation values, multiplied it by this weight matrix, and then finally doing the same thing for the output layer. Okay. So to validate that, what I'll do is I'll open up an Excel sheet or a LibreCalc Excel sheet and try to do it manually. Okay, let's see. New file, new spreadsheet. Okay, and the idea is I have these bunch of values, right? And I'll try to multiply them as 1, 0, 1. So this one is from the input to the first hidden layer, or rather, since it's just a 3 to 1, since it's just a 3 to 1 architecture for the neural network, then it's just from input to hidden, right? So this one will serve as my input layer. So let me just, how do I color these? Background color, right? So yellow will be the input layer, and then this will be my weight matrix. Let me see if I can actually copy this, paste it here. Tab, not comma, or space. Oh. Let's see if this works. Oh no, it didn't work. But I got 282.199, which is this part, and then this part as well. So let's copy this manually. Okay, so this will be my weight matrix. Okay, randomly generated weight matrix. So the idea is if I multiply these and put a sum, the resulting values should be, well, not equal to this, because these are not equal to this, because these are equal to the activated values, right? But rather it's unactivated values, right? So to validate that, I just simply activate it, and it should give me the same values as the one in the console. So I'll tag this as the color blue, sky blue, right? So yellow for the input and light blue for the output. Okay, so this one would be something like this cell times this cell plus this cell times this cell plus this cell times this cell, right? And then I have that value right there, which is the raw value. Okay, and then which is what our program is doing. It's taking the input, doing some matrix multiplication, and multiplying it against the weight matrix for this particular column. Same goes for this one. So what I can actually do is I think I can anchor these cells right here. Right, and then just drag it right here. Right, so it will be the same formula, taking this input vector, multiplying against this weight matrix, and then summing everything together. And then on row 2, I'll activate those values. Again, the formula for our activation was, let's see, in our matrix implementation. Oops, sorry. Or rather, I think it was in our, was it in our matrix? Or I think it was in our neuron implementation, right? Every time we set a new value, it activates that value, and the activation function is given by that raw value all over 1 plus the absolute value of that given value, right? So it's a fast sigmoid function implementation. So it's this value, whatever that value is, over 1 plus the absolute value of that value, right? If we drag it here, it will perform the same calculation, right? So if you look at the output, then it's almost the same. prior to precision, right? We almost got the same value: 514079, 514078, rounding it to 79. Same goes for this one: 503373, 503373. Right? And what happens here is that this one gets multiplied to this weight matrix to get the final output of a 3-to-1 topology. So what we do is, from this time, from the hidden layer to the output layer. Okay, so what we can actually do is we can just reference those values and put it in a nice column right here, and then copy the weight matrix. So this, just to maintain consistency, this one will be the color yellow. Okay, hopefully it's the same color, and the weight matrix will be these two numbers right here. Okay. And this will be the color sky blue 2. Sky blue 2. I think it's this one. Right, and then the operation stays the same. The value is equal to this cell times this cell plus this cell times this cell. Okay, and then we activate it by taking that value over 1 plus the absolute value of that value, which will give us 0.19131137. 0.19131137. So regardless of precision, then the values are actually the same, right? So what we did here in this devlog is that we wrapped up the feed-forward function, wherein we have a neural network class. Wherein the feed-forward function is performed by looping through all the layers until layers.size -1. Again, we do this because we want to get the weight matrix, which is only until the index of layers.size -1. Okay. And then we take the first matrix as the input. If we're inside the input layer, then we take the raw values via the function getNeuron matrix. If we're not inside the input layer, meaning if index I is not equal to 0, then we get the activated versions of those neurons for some layer at index I, which returns the matrix form of the activated version of this layer. The matrix B, the second matrix, will be the weight matrix at index I, since it uses the same counter. Okay. And then we get a new resulting matrix by multiplying both matrices using our command pattern multiply matrix class. Right? And then setting the result of that matrix as the neuron value for the next layer, which is at index I plus 1. So this way we won't fall into a index out of bounds exception when we loop through this particular part. Okay, C index will be the column index for the columns for this resulting matrix, which will always be a matrix of row size 1. So we can always access that first index of the row wise for this matrix C, which is at index 0, and accessing the column index using C index, getting its value, storing it as the neuron value at layer I plus 1. Iteratively, this will proceed until it reaches the output layer, thus resulting to a feed-forward approach in neural networks. So the next thing we'll try to do, probably in the next video, will be to perform backpropagation, wherein we'll adjust the weights. Right? We'll adjust the weights for the neural network based on some error term. Okay, we'll probably divide it into 2 more videos. One video for computing the error term, and the second video is dissecting the backpropagation algorithm. Okay, so that's it for this devlog. Before we end, we are going to commit the changes and say something like feed forward function for neural network class. Commit, push, Oh, wrong password. Right. So for anyone trying to follow the devlogs video, you can access the progress at this git link, rlmpy/ann.git. So if we refresh this, right, our commits should have entered there. Feed forward function for neural network class. Okay, so that's it for this devlog, and I hope to create another video soon.